Yeah, so welcome to London Retro Computing, everyone. I'm Dave Snowden. I'm the admin of the group. So I guess for those who are new, the idea really is to get together people who have an interest in retro computing, and that might be people who have old machines, from the sort of 1980s, and are still using those. So sort of Spectrums, BBCs, Commodores, or pets and the like. And it also could be people who are actually building new machines with sort of 1980s tech. So I'll be looking at people who are using sort of the RC 2014 or some of Steve Cousins machines, or who are just building their own. And the idea of this group really is to sort of encompass both, camps of people. The people who are generally interested in 90s, 80s tech, and whether that's both the actual old machines or building new machines and doing new stuff with new hardware. So this is the fourth meetup I think we've had. We've had a fairly lengthy hiatus where Steve, our speaker today, was due to give a talk a while ago, but obviously with the COVID restrictions, that got postponed. And it took me a while to get around to organising some online meetups. Hopefully this will not be the last. So I'm going to hand over to Steve. So a bit of housekeeping. I'm going to mute everyone while Steve is talking, just to keep any background noise down. And so if you wish to ask a question, it might be easier to leave it to the end, but remember to unmute yourself. Okay, so I'm just going to unmute Steve, and then I'll let Steve introduce himself, as he's much more to do a better job of it than I will. So over to you, Steve.
Thank you very much. Right, if I'm all unmuted, well, I should probably remove the... Hello, everyone. I shall share my screen so you can see some kind of slides, because I spent time preparing them. It would be a waste to not use them. There we go. So, hello. As the top part of the slide says, my name is Steve. As the bottom part of the slide says, I'm a little bit of a geek. And if we've all Zoom bombed to the right meeting, for the next 20 minutes or half an hour, I'm going to be talking about Ada Lovelace and the very first computer program. So over the course of the next few moments, I'm going to be going through what that first program was. I'm going to have a look at it. I'm going to explain how it works, what it does. I'm then going to go through a brief process where I transform that original program into some JavaScript so it becomes potentially more understandable. And then I'll finish up on the perpetual debate of, was Ada really the very first programmer? So without any ado, we will start, as all talks start, with the who am I? What have I done? What's my deal? How do I deserve to be on this stage, as it were? So we have a who am I slide, or as it should probably be called, the ego slide, where the speaker gets to bang on about themselves for 10 minutes. Well, I'm not going to do that because I haven't done that much. I'm a developer by trade. I've always been a developer. I've done game stuff, I've done ed tech, I've done all sorts of random things. I've done a few emulators in my time, which is where my initial interest into retro comes from. I also wrote the emulation framework, EMF, which is on my favorite domain ever, which is em.ulat.es. But it's quite an old thing and I keep meaning to update it. But what's mostly important about the who am I slide is what's not on this list. I'm not a computer historian. I don't work for the British Library. I don't work for the Science Museum. I do help out at the Computer Museum in Cambridge, but that's a helper. I'm not a doctor of computer science programming type of things, which means one thing. Everything that goes on in this talk, everything that I've learned here, everything that I'm going to demonstrate and show you, I have done myself in my spare time, just for someone that likes reading this sort of stuff and likes learning about stuff, which is a very long-winded way of saying, if I can do it, anyone can do it, because it doesn't require any particular special skills or any background. So with that in mind, what was the first program? Let's have a look. It's that. That's the very first program to ever exist. And we'll come to the issues later. So this you can probably have a look at, and you can probably take a pretty wild guess at what's going on. It's got a series of lines, so you can say, well, those are the instructions, that's what's going on. There's some columns indicating something, and it's not very long. There's only 25 lines. Through this and understand it. But we'll start off with, well, where was it for a start? If you, I don't know who can read this, at the very top, diagram for the computation by the engine of the numbers of Bernoulli, see note G. So this program was an appendix in a book written by a guy called Luigi Menabrea, or Menabrea. Luigi Menabrea, as the name suggests, was Italian. He'd written a book that describes the analytical engine by Charles Babbage. This was written by him, obviously, but then translated into English by Ada Lovelace, Ada King as she was formerly known. So this was an appendix in a translated work. Also, as we said at the top, diagram for the computation by the engine, that's the analytic engine, of the numbers of Bernoulli, or Bernoulli numbers, see note G. When Ada translated this work into English, she added a whole series of extra notes to the original text, explaining and expanding on the words that Luigi had already written. Note G covered some ideas of algorithms, and to supplement those ideas, in note G, she created an appendix, this, the first program. Now you can see from this that it's an appendix to a note of a translation of another work that was read by probably 10 people. It's understandable that no one really knew of Ada's contribution to the world of programming until much later. But here it is, appendix to note G, the first program. So what did it do? Well, as it says at the top, it computes Bernoulli numbers, the numbers of Bernoulli. And these are Bernoulli numbers. They look like fractions, they are fractions, and there is nothing particularly special about them. You will notice at the top out that there's no third Bernoulli number or fifth Bernoulli number. That's a bit of a lie, there is, but the third, the fifth, the seventh, and every odd Bernoulli number is a 0, except for one. Every other Bernoulli number is a 0, so that's not very interesting. So they're not represented on this list. It also means that sometimes if you're looking at work, particularly maths papers that discuss Bernoulli numbers, they will sometimes use Bernoulli number 2, second Bernoulli number, fourth Bernoulli number, to use the numbers on the top. But sometimes they'll just say, well, since the third one doesn't exist, we'll call the fourth one the third one. It can get confusing, so every now and again you'll see that they will get mixed up. But the thing that's noticeable here is that these fractions, as nice as they are, don't really follow a pattern. Well, there's no discernible pattern. So it's not something we can obviously compute. We have to go through the manual workings to try and work out what each Bernoulli number is. Now, Bernoulli numbers are used in various mathematical things. They're used in Taylor series expansions, for example. Civil engineers use them. They're also used in Riemann zeta functions to compute primes and subsequent primes. So they've got a lot of uses in mathematics, but obviously with the numbers not being very regular, you have to compute each and every number. Now, for those of you on the call who are even older than I am, which is probably not many of you, you may remember when you went to school, you may have had a book of log tables. So to do natural logarithms, you'd have a little book and you'd look them up and you'd say, all right, this is the logarithm I need and this is the logarithm. They were computed by humans, they were then written down into tables and then sold as books. People didn't have calculators, so the calculator at the time was a human. The same way as back in the 60s. A computer was a human that did mathematics. You may have seen the film Hidden Figures, which focuses on some of these computers, the human computers. So back in the 1800s, a human would have computed the Bernoulli numbers and then published them as a printed pamphlet, so mathematicians didn't have to compute this series of fractions. But you never know, maybe the decimal form of these fractions is a little more understandable and has a little bit of better pattern. No, not at all. The decimals are still incongruent. There's no way you'd actually be able to guess, so you have to work out every single number. And what better to compute a series of numbers than a machine? So how are these numbers calculated? Well, it's a fractional thing. And the fractional thing is that. Now, the mathematicians amongst you will have no problem with this. You can probably do it in your head. For the rest of us mortals, we probably do the best we can, and we probably notice a pattern. We notice B1, B3, B5, so obviously the Bernoulli numbers are in here. We also notice each of them is multiplied by a fraction. And we also notice that the component on the top, the numerator, changes each time. It goes from 2n to 2n times 2n minus 1 times 2n minus 2. Then that appears in the next part, but multiplied by 2n minus 3 times 2n minus 4. The same with the denominator. It goes from 2 to 2 minus 3 minus 4, 2 times 3 times 4 to 2 times 3 times 4 times 5 times 6. So it's very easy to see there's a pattern here, and it's a very obvious logical pattern. So it'd be very easy to write a piece of program code that would do this. Unfortunately for Ada, she had to wait for someone to invent a computer first. But if we reduce this, if we look at each of those parts of the equation and we look what B1 is multiplied by and what B3, we can reduce this equation to something that looks a little simpler. It isn't that much simpler, to be fair, but we've moved the complexity away. And as I'm sure you remember from maths, if you want to rearrange the equation, you subtract something from one side, you subtract it from the other. So it's then very easy to compute the Bernoulli number for, say, B2n minus 1 by moving it to the other side to give us this. Now this shows us something very special about the Bernoulli numbers. It's also true of Fibonacci numbers. To compute the fifth Bernoulli number, for example, shown in the second half, you need to know the first Bernoulli number and the third Bernoulli number. To compute the seventh, you need to know the first and the third and the fifth. To compute the ninth, you need the first, the third, and the fifth. You're way ahead of me. So you obviously need some kind of memory to know all of the previous Bernoulli numbers. So with this series of steps, you can see it's a very programmatic approach. Programmatic in the modern sense of the word, obviously. So we can see that if we were programming it now, it would be a very simple process to pump this into a piece of code and churn out the result. So how did her program actually do it? Well, let's go back to the code again. Okay, let's take it line by line. That might make things a little simpler. So I've tried to zoom in on the bottom half here. Hopefully that's legible. I'll read out as we go. So first off, in the left-hand column, we have the number of the operation. 1, 2, 3, 4, and so on. It's nothing more complex than that. It's just like writing basic programs, except when we are writing basic, we generally begin with the line number 10, followed by the line number 20, just so if we'd forgot anything, we could slip it in line 15. But the number of operation, nothing more complex than just an ordinary ordinal number increasing sequentially from 1. Second is the nature of the operation. In this case, line 1 is a multiplication sign. There were 4 operators in this programming language. There was addition, multiplication, subtraction, and division. Nothing else, not even assignment. And that's something that's important, and we'll come back to that in a moment. So we've got 4 operations here, the basic maths, and the third column, variables acted upon, show us how that operator works. So in this case, it says V2 times V3. Very simple operation, basic multiplication. You'll notice there's a small number 1 as a superscript on the left-hand side of each V. That indicates the number of times this variable has changed. Now, why is that important? Well, to a programmer, it's not really that important. But if you're trying to debug or you're trying to trace through, or in her case, you're doing a dry run of the program on paper, simulating it, this is very important because if you can see how many times a variable has changed, you know whether it will have the value you expect it to, or whether something else has changed that variable that you didn't spot. So it's actually quite useful. It's almost like she'd invented breakpoints 200 years before they happened. Fourth column, variables receiving results. The answer. We perform v2 times v3. Where do we copy it? Well, here it says v4, v5, v6. It copies it to all of them. We said there's no assignment operator. And if you've got a series of gears, which the analytical engine had planned to be, a lot of gears rotating each time just to copy this column of numbers to that column is a very expensive operation. And if you think about it, assignment is a wasted operation. Every time you assign something into a variable, you're saying, I didn't put this in the right place in the first time, so I'm going to do it again now. So what this program does is you say, I'm going to perform the multiplication, and then I'll copy that result to 3 different places at once. I'll copy it to V4 and V5 and V6 all at the same time. Excellent little piece of move. Next column, indication of change in the value of any variable. Remember I said there are these superscripts that indicate whether this is the first time the variable has changed or the second time and so on. This column keeps a tab on how many times each of those variables has changed. That's all that is. And statement of results. 2n, it's multiplying value of 2, a value in register 2, a variable 2, by the value in variable 3. And that does the equivalent of 2n. Statement of results is really a comment in this case. And I'm sure we all put comments in our code, so you all recognize that statement of results as her way of putting a comment in. On the right-hand side, it says data. These are all the variables, and it indicates what's in that variable at any one time. At the top, it indicates the variables with variable names, i.e. v2, v3, v4, and so on. And in the row alongside instruction 1, it indicates what's in that variable. Not as an actual number, but as the intent, as a comment saying, after we've done this operation, this variable should contain this result, 2n, for example. And you can see the last 3 columns there all indicate 2n, indicating that v2 times v3 has been written into v4, v5, and v6. So although it's quite an old program, you can see a lot of the fundamentals are still there. And it is still very easy to work through. So what about the initialization? Every program needs to initialize itself somehow. So where here is there a piece of program code that says initialize this variable? And the answer is it isn't anywhere. There's no assignments. So there is no way of writing code to do the initialization. What there is instead is about middle top on your screen there if I'm looking at mine. And it looks like that. It's the data section that we saw before. So before you run this program, you would have to rotate the gears in the analytical engine, in the theoretical analytical engine, so that variable 1 would represent the number 1, variable 2 would represent the variable 2, and variable 3 would represent the number of the Bernoulli series that you wanted to compute. In this case, we'll say 4. A lot of esoteric languages use this trick as well. There's only 4 instructions in this programming language, but there are programming languages out there that only have 1 instruction. And that is possible because there are a number of variables and memory locations which have been predefined with numbers, with constants. And because they're not going to change, you can rely on v1 to always be 1. That way you can simulate the idea of an assignment or a copy or something else because you know there's always a 1 in that column. So with that in mind, let's look at the first few lines of program code. Here are the first 9 lines or so. First line we've covered, v2 times v3. Second line, 2. Subtraction, v4 minus v3. Simple enough. So we know v1 has been a constant. It's always 1. It starts as 1 at the beginning. And v1 is never changed throughout this program. So it always maintains itself as 1. So that means at the end of the second line, v4 is 2n minus 1. As you can see, that's in the comment on the right. Third instruction's addition. v5 plus v6, I think that says. v5 plus v1. That result goes into v5. You can see here it says 2v5 because this is the second time we've changed v5, as it is the second time we've changed v4. This computes 2n plus 1. Next, v4 divide, sorry, line 4 divide, v5 divided by v4, that's 2n minus 1 divided by 2n plus 1. And you can see, hang on, wait a minute. v4 is 2n minus 1. v5 is 2n plus 1. So v5, 2n plus 1 divided by v4 should mean the comment says 2n plus 1 divided by 2n minus 1. Unless there's something I'm missing. This is not only the first example of a computer program, this is the first example of a computer bug. We get 4 lines in and Ada's made a mistake, or at least someone's made a mistake. But at this point, as I was working through this, I didn't know which it was. I had seen this program, you know, on various computer science walls and in museums. I'd never really studied it until I started this little project. And no one had thought to correct it. There was no graffiti, there's no pencil mark saying, by the way, error line 4. So I didn't know whether the instruction was wrong, and it actually should have read v4 divided by v5, or whether the comment was wrong. It turns out after going through this, that actually the comment is right and the program code is wrong. So in the process of simulating this and transforming it, that was the first bug that I had to fix. But as you can see, line 5, v11 divided by v2 goes into 11. It makes sense that it's 2n minus 1 divided by 2n plus 1, because otherwise this equation doesn't make sense. Because at this point, I'm matching this program code up with the original mathematics and working it through by hand. Line 6, subtractions, everything else is pretty straightforward at this point. And because I've got that far, I thought I should write a simulator. Now, for those that aren't JavaScript programmers, I'm not going to go too into the semantics of JavaScript. It's more about the shape of the code here. And the code here is no different to any emulator that you might have written or seen. You have a series of program instructions. This is just a copy of exactly the same as what Ada wrote. As you can see, multiply v2 by v3 and write the result into v4, v5, and v6. This has the equivalent of computing 2n. And these are the first 5 lines of that program. I can then write a very simple simulator, which simply goes through each line of code with a basic program counter, perform the operation, and then write it back into each destination variable. You'll notice I've called this destination variable mil. This is a piece of terminology that Ada did use in the day and was also used in computation at the time to mean accumulator. This is a temporary result that we're going to put somewhere else. And then increment the program counter and do it all again. So anyone remember this? To compute the 5th Bernoulli number, we need to know the 1st and the 3rd, and to compute the 5th, we need the 1st, the 3rd, and the 5th. Well, there was no mention of that in the program code that we just looked at. So let's go back. And right here, between line 23 and line 24, there is the invention of the loop. Here follows a repetition of operations 13 to 23. That single line pretty much born the whole industry. But there's a little problem here. I don't know if anyone spotted it, but on line 23, we write the result into V10. We do a subtraction. The line 23 says subtract. Take V10 and subtract V1. Well, we know that V1 is always going to be 1. So essentially, we're doing a sort of negation at this point. which is what's necessary because of the way the rest of the computation has been built. And that's all fine. But the result is going into V10. If we do a repetition of operations 13 to 23, we need V10 when we compute the next Bernoulli number. And when we compute the Bernoulli number after that, we'll need V10 and probably V11 and then V12. So how does that work? Well, the answer is it doesn't. Every single variable that you have seen in that program is a constant. There is no other way of changing it. Ada had the right idea. The program code and the data should be kept separate, and there should be no way of dynamically changing the code. There should be no way of running data as if it were code. She'd got that idea right. But if they're all constant, then how do we store data? How do we move through? And the answer is we can't. Referring to variables 10 through 15 as an array, there's no way of changing that either in the program code or in the variable state. So basically, this is the very first example of Stack Overflow, where someone is copy and pasting code, but not understanding how it all works. Essentially, if this program were to work back in the 1800s, you would have to copy instructions 13 to 23, and then change every variable 10 to variable 11. If you wanted to compute the Bernoulli number after that, you'd have to change every variable 11 to variable 12, and so on and so on and so on. So in that sense, it would never really work as a program to compute Bernoulli numbers. But I'm halfway through this now. I've been translating this into JavaScript. I will have to come up with a solution, and I'll show you the solution in a moment. But until I got there, I was still computing the very first Bernoulli number, so I only needed to run the loop once. So I knew that would work. So as you see, I had the program instruction, the operation multiply 2 by 3. I then started to replace that with variables, with an array of hard-coded indices. By reading the comments, I knew that variable 4 was always 2n minus 1. So I decided to call the index of the V array n2, n1 for n times 2 minus 1, for the obvious programmer reason that you can't start a variable name beginning with 2 or any numeral. So that's 2n minus 1 equals 2n plus 1 equals whatever 6 is meant to be, and so forth. And I come up with extra variable names as I went on. As I understood the program better, I would say, oh yes, that mil variable, that's the accumulating total for the Bernoulli numbers. This is my numerator, this is my denominator. And as you can see, over a couple of transformations, I got genuine variable names. Now, I'm sure we all use proper variable names in our programs. I'm sure we all have long variable names and not things like I and J. But here you can see it's very explicit what is going on. The only change that I've created here is that I have an index to result. I realized that as every time I went through the loop, I would need to write the result into a different memory location. I would create my own little index, which was my hack on working around the problems in that first program. But I think there should be enough there. And by the way, all of these program snippets, I'll go back to that slide. If you'd like to see the original program that I simulated, which is all JavaScript, and each of the 5 or 6 steps that I took to transform that original simulated program into a nice, clean JavaScript program, then the URL on the bottom of your screen will show you what I did. It may not be the best way of doing it, it may not be the quickest, but I think it lets everyone see exactly what's going on. Even people have a casual interest in maybe scripting of some description. I think it's simple enough for everyone to be able to follow along and understand how she wrote that program. So we come to the contentious part of the evening. So was she really that first programmer? I consider the first programmer because why wouldn't I? But there was always the nagging doubt and a lot of suspicions and a lot of diatribe online that she might not have been the first programmer. And there's a lot of people out there who are willing to argue against this notion. I mean, we've already seen the code has a bug in it. Not just any bug, a bug at line 4. We've barely started and already it's broken. Now, granted, it's probably a print error, not a her error, because the rest of the maths works, the rest of the program works. And let's face it, at the time, the printers wouldn't understand programming. Maybe printers still don't understand programming, but with desktop publishing, that's less of an issue nowadays. Numbers. It's only really mathematicians and engineers that would have understood what a Bernoulli number was and why it was useful. So obviously the type of people who are reading this book are already going to be quite educated. They would probably spot that straight away. But still, it's an error. And, you know, whoever is without sin casts the first stone. Whichever programmer has written code without bugs in it, yeah, I personally haven't met any. So we probably shouldn't be casting shade on programmers who create bugs, especially one that pertains to be the very first programmer. If we have a bug, we just change a line, we run it again, we can see if there's a problem. Ada didn't even have a computer to run it on. So she'd have no way of knowing if it was really working or not. She'd have to do it by hand, line by line, number by number. And that could be quite a lot of computation. Second reason why she might not be considered the first programmer, that notation is problematic. There's a lot of things in there which is like, well, do you really need that? You know, the postscript notation, the postscript notation of this is the second time the variable has changed. Is that something a programming language would ever really have? Current programming languages don't have them. She also starts numbering at 1. As a programmer, I've been programming for 40 odd years now. That probably does age me, I know. But in my real life, I find it very difficult to count from 1 now. She counted from 1. But there are other programming languages that count from 1. Ada, the language written and named for Ada Lovelace, that counts from 1. Fortran, I think, counts from 1. A lot of languages whose main work is mathematics or calculation in some way, engineering languages, they also count from 1, not from 0. The 0 that we all expect languages to start from, like to start from 1. So maybe after all, we've got it wrong. The assumptions that we make about programming, that it should start from 0, that it should express this, it should express that. We might be wrong. Maybe you had it right. Maybe Ada had it right. So maybe we shouldn't be complaining about the notation just yet. The loop. Here follows a repetition of operations 13 to 23. This is probably the programmer's equivalent of Linus Torvalds, I'm building a kernel, it's just for fun. Here's just for fun. We could mirror that in here follows a repetition of operations 13 to 23. The first loop, the first idea that the machine is going to repeat this, but in a slightly different way. Unfortunately, the loop that she invented didn't work. What's the point of inventing a terminology and a language and a whole new industry if it doesn't actually work? You haven't invented at that point, you've just had an idea. Also, as we've said, she was translating Luigi Menabrau's work. So does that count? I mean, she did write an awful lot of that translation. I don't just mean the translation part. She added probably about 40%, 50% of the physical total of that book. And that includes the note, and that includes the appendices, especially the one that we're looking at here. So it's more than just a blind translation of someone's work. It required someone who understood content to be able to translate it. And it requires someone that really understood the work to be able to write additional paragraphs, additional chapters, additional notes, and an appendix such as this. And of course, how can she be the first programmer? Babbage didn't even build the machine, and he would have already designed programs himself for his own machine. Yes, but the things that he wrote would have been the equivalent of Hello World. It would have added 2 numbers up. This program is the first program that actually does something significant. It's a non-trivial program. And to that, it means it really is the first program. Well, at least it should be. So I tried all of this and I still wasn't sure if people were buying into it. Everyone I was looking online and everyone was sort of giving negative reasons of why she wasn't the first programmer. She wasn't the first programmer because it has a bug. She wasn't the first programmer because it doesn't work. No one's being positive. I know that's the internet, but no one on the internet was being positive about why should she be the first programmer. So I had to think about this. And I thought, I need an argument. I just need one argument. That'll do me. Just one argument of why should she be the first programmer. One positive reason why she is. So I thought, if this work had been done by a man, would he be considered the first programmer? And I thought, and it's like, yes, of course he was. And if that would have been done by a man and he'd been considered the first programmer, therefore, Ada must be the first programmer. And this must be the first program. Translate in that sense, despite the bugs. So we've seen that first program. We've looked at it, we know where it comes from, and we know it did decimal approximations of Bernoulli numbers. The analytical engine as designed was the same as the difference engine in as much as each number was represented by a series of cogs on a big spindle, and these numbers would rotate. So it was always a decimal approximation. The computation program that she wrote also creates a decimal approximation based on the idea that the numbers in the machine would be decimal numbers. The algorithm was Bernoulli numbers. I don't know why she chose Bernoulli numbers as the first program. It doesn't to demonstrate storage, computation, loops. There's a proper description in there. And as we said, we've established that Ada was the first programmer and we really should attribute that to her. So with that in mind, I'll thank you for your attention. The links on screen, the first one should give you the breakdown of the original code into JavaScript. The second link, code Ada 99. This is the reference to another thing that I did relating to this first program. There were lots of ways of computing Bernoulli numbers. More than this one. It was more interesting to program, basically. And I've started writing that in lots and lots of different programming languages. I think I'm up to about 24 or 25 different languages at the moment. It might be amusing that so that if you don't really get JavaScript bit, you can go and compute Bernoulli numbers using one of the other languages. So with that in mind, I shall flip back so I can see your lovely faces and take any questions that you may have.
Great, thanks, Steve. I'll start off, if I may. So you mentioned that Babbage had probably written some programs himself. Is that not known, or?
Well, he has notes in his in the Luigi book and elsewhere. There are notes for what he would say. This is how you do this. If you're going to do multiply, this is the way you'd multiply two numbers in the engine. I'm not convinced that constitutes a program. It's a program as much as it's an instruction, but you need more than one and two instructions to actually do something significant.
Okay, so he was more sort of documenting the instruction set rather than actually writing anything using that instruction set.
Yeah.
And okay, cool.
It'd be like if I can step away. But this is not intentionally on my floor because of this, but some program the Z80, because I've been doing some work on ZX81s recently. It'd be the equivalent of saying that Rodney Zacks is a programmer. He is a programmer. He can program, but nothing in here would constitute an actual program. It's examples and sort of documentation, API writing, essentially.
Cool. Yeah, that makes sense. So anyone else? Remember, if you want to ask Steve a question, you need to unmute yourself. Don't be shy. I'm assuming people can unmute yourselves. If you are trying to and you're failing, write in the chat and I'll unmute you. But for now, I'm going to assume that you can. Go on.
Did I avoid the religious war, by the way? I can see in the chat, John Hearns has written, Julia Fortran, religious war in 3, 2, 1. Right, so questions come through in chat from Ubuntu. I was wondering about the choice of JavaScript. Was there a specific reason or just for fun? So I've been doing a lot of JavaScript recently, not on the ZX81, I should probably mention. Although I do have the idea in my head that I should try and port JavaScript to the ZX81. I think that would be ludicrous. But when I first started looking at this first program, this was a couple of years ago now, 2, 3, maybe even 4 years, depending on whether or not you count 2020 as an actual year, I suppose. So when I started looking at it, I was doing a lot of JavaScript, and I thought, wouldn't it be fun if I rewrote the very first program in JavaScript? It's my language of the day, it's the thing I'm doing. Let me rewrite it in JavaScript. A friend of mine, I posted this up on Facebook, obviously, because I'm a like whore, and I got some likes and some comments, and one of my friends said, why don't you write that in Ada? It was, after all, a language named for Ada Lovelace, so why don't you write that program in Ada? So I took a lunch break and I did. So I'd then written this program in JavaScript and then in Ada, and then I wrote it in 24, 25 other languages. With all of that behind me, when I started simulating the analytical engine, it just seemed natural to go for JavaScript because it means I could run it in the browser, other people could see it running. If people wanted to build a nice IDE around it and have a picture of the analytical engine and simulate the codes, they've already got the first program there, fully debugged, to demonstrate the workings. And I think there is somebody's law that says every program will get rewritten into JavaScript at some point. So I just decided to cut out the middle person and write it straight in JavaScript first time around. Yes, I'm an equal opportunities programmer. All languages are created equally, just JavaScript is created more equally than others. Come on, that's got to get someone angry enough to ask a question.
Do you think that any of the concepts that she proposed in the program actually got taken up anywhere? I mean, is it true that it was actually totally forgotten about, and basically the inventions of the next, I guess, COBOL was probably the first programming language, real programming language? I don't know, Fortran. Is there anything that carries over into sort of very early programming languages, takes in that, or is it completely starting from scratch, do you think?
Because every programming language of her era, i.e. hers, and all of the ones that started, which would probably include APL, which is short for A Programming Language, as well as Fortran, as you mentioned, and COBOL, they were all there to solve mathematics equations, often for engineering of some description. Is the core of all the languages at that time. That is what they were focused on. Nowadays, you'd have a language that was maybe focused on web frameworks, for example, and it's very geared towards that. But all of those earlier languages all base their ideas on maths. So even if they didn't know of Ada's original work, they would come to the same or very similar conclusions about how it would have to work in order for a series of instructions to generate a result. I mean, you do touch on a point there on the numbers in the programming language, because that's what it was there for. It's, you know, they're all numbers. in her work, which includes other things than just that very first algorithm, she speculated that although this computer was computing numbers for the sake of computing numbers, there's no reason why numbers couldn't represent something else. This was an idea that she expressed back in the 1800s. She said, why can't these numbers represent musical notes? And it took until the 1980s before we had MIDI, where, you know, middle C is the number 60. The D above middle C is 62. These notes have a number. This was an idea that she'd already expressed 160 years beforehand. She also wondered about whether these numbers could represent letters or words, predating ASCII by another 130 years or so. And because although she was estranged from her father, Lord Byron, she still had a poetic sense to her. So she wondered whether a computer could write poetry, because the numbers could represent words and stanzas. And now with AI coming to the fore, with AI-based languages, we're now realizing some of her original ideas on, well, a computer can create poetry because at the end of the day, it's just numbers, isn't it? And whether the numbers are manipulated by her programming language or by a Fortran programming language or by an AI type language, it's all doing the same kind of manipulations under the hood. So another question that's come up, can you actually run loops on an analytical engine? No, you can't, because the analytical engine never existed. He never got to build it. Babbage was kind of the hero of hardware people for me, because he was very annoying. He was very hard to get along with. He would treat everyone like an idiot and would probably tell you to your face. As a consequence, he found it very difficult to get funding. So when his funding ran out for, I think, the second time or maybe the third time, he couldn't get any more money out of the government. So the engine was never built. There's bits of it and there's gears in the section, but it was never finished at all, really. It was, you know, parts on a work floor. So the program was never run. It was never able to run the loops, and we're never able to pick up that bug. So he was famous for that, I guess. Another question from Geordie. You affirm that Ada is not considered a program because she is a woman. Is this correct? Have evidence? Well, there were other men who, prior to this becoming well known, as I said, her work is in an appendix of a note of a translation. There were other people who had done translations of similar work. There were other people who came later who had referenced the work, and they had been referenced as programmers. Now, of course, you can never understand what's going on in someone's mind at any point. But if all of these other men were considered programmers, even though they came later, then is that because they just didn't know about Ada, or because they were purposely excluding her? And we're not going to know. All we know is what they've written down. The people are long gone now. The books are essentially from the early 1900s is all we have left of their contribution to computer science. So all we can do is do what historians would do, is to look at the source material, try and understand what was society like, what were they like, to try and say, well, realistically, on balance, would they have considered her as a programmer? And it's very unlikely they would have done. Even if the war was more important. Yes. Richard has started typing a question and then unfortunately not finished. Thank you, Richard, you finished. You said that her program... Good question. So the program was never technically lost. It was always in the book. Some of you that are on this call are actually friends of mine, so you'll know that in my other life I'm a magician. And magicians have a saying, which is the easiest way to keep a secret is to put it in a book. Because once it's in a book, it goes on a shelf and it gets forgotten about. No one ever looks there. This was never forgotten. This program was always in the book. It was always on the shelf, just no one actually bothered to read it. And it wasn't until some bloke called Alan Turing, that you may be aware of, he was, obviously rather quite a bright chap. And when he was doing his work, he referenced a lot of the old material, which included this book. So he came to realize that, this work's been done before. And he started quoting it, as well as his peers at the time. And as a consequence of him quoting it, people started looking back and said, oh, right, well, if Alan thinks this is good, I probably think it's good as well. I'll go and have a look. And so it received a renaissance sort of back in the 50s from his paper on computable numbers, probably, that, it might be an old book, it might be dusty, and you might have to go to the British Library to find a copy. But the book exists, the material exists, go and rediscover it. And then, obviously, as his popularity grew, the references to his paper grew, so therefore the references to her papers grew, and it became rediscovered, as it were.
Okay, I'm going to have another attempt at igniting a flame war. So you've written Ada's program in 24 languages. Do you have of those 24, do you have a most preferred and a least preferred?
Oh, you really want to start this flame war, don't you? My most preferred, probably, it's between Ada and JavaScript, partly because JavaScript was the first one I did, and I thought, oh, this is quite nice. It's now in a form that is very understandable. I can show this to people, and I can say, look, be excited by Ada's work. And obviously Ada, because the language was named for her, it felt very right that it should have been written in her language. But my favorite language is always the one I'm going to do next, because that's the one that holds some excitement for me. It's the unknown. What can I discover? For me, I've given a talk, by the way, not that I'm trying to plug it, but I gave a talk in Paris a few years ago where I went through these different programming languages that I'd written, and judging by the people in the audience going, ew, my favorite is Bash, because I managed to make the most people go, ooh, because it's Bash. This is for munging files and text. This is not for doing hardcore mathematics. And the fact that I'd managed to massage it into doing some maths annoyed enough people that I like doing it for that reason alone. But the most complex one for me to write was Forth. I'm not a great Forth programmer, although today it's May the 4th. So, I feel like we should be talking about Forth perhaps and the Jupiter race. But Forth is not very, at least not this particular algorithm. This algorithm, Forth works on a reverse Polish notation. You push stuff onto the stack, you perform the operation, and you take stuff off. So handling a block of memory so you can go back to the first binary, the third binary, and the fifth binary, for example, it's not easy when there's a stack of numbers and you need to get to the numbers at the bottom. So you have to use a different data type for that, which I wasn't very aware of, because I'm not a great Forth programmer, as I say. So there were a lot of issues with that and the computation that really didn't suit it to Forth. Very clever tricks to fix it. But until they do, Forth is my most disliked implementation, and Bash because it annoys more people than any other. Except for Perl, according to Shane O'Neill. That's okay, I did Perl as well, but it can't be any slower than Java.
Oh, nice try.
Yep. May the 4th retro launch.
Ooh.
I won't click the link in case it breaks my machine, but there's something there to look. Yeah, as a completely side point on Forth, while no one is asking questions, 5 years ago, and I looked it up today, so I know it's 5 years, I wrote a Forth interpreter in JavaScript on May the 4th. And obviously I called it Jedi Forth.
As you would, obviously.
Yes.
Yeah.
That should give people a breathing space to find some questions.
Okay, well, I think if no one feels need to speak up, nope, still no one. Well, thanks very much, Steve. That's much appreciated. And like I said, we would like to do this again. So if you would like to speak, you've seen that Steve survived, and nothing virtual or otherwise has been thrown at him. So it's you could do this too. So if you would like to talk about a retro computing project or of yours, or just demo some hardware you've got that might be slightly unusual, please give me a shout via Meetup. Otherwise, thanks again, Steve. It's been much appreciated.
No, thank you. You're welcome.
Okay. With that, then I'll close the meeting and the recording. I'll share the recording link afterwards. Thanks all.